So what is the setting? So first I want to do a wrong definition of Tambara functors to give you some idea what they are. This is not a definition, but maybe you get some idea what they are. And then I want to explain what Loday constructions are, then merge the two, and most importantly, talk about 3 examples. I hope I get to that. Let's see. So for today, G is just a finite group. So I will not say this again, and rings are commutative with unit and associative. I will also not say this anymore. Well, I will say it once now in the definition, but then that's it. So this will be fun. So the definition, or the pseudo definition I give you, is probably closest to the original one by Tambara. So if you miss some details, just check it up with him. And of course, he didn't call them Tambara functors. He's Japanese, so he's very, very moderate. So they are called T and R functors. In his world, trace norm restriction. So if you know what a Mackey functor is, just think about having a multiplication on top of everything and having multiplicative norms. If you don't know what a Mackey functor is, then, oh dear, we'll get to that. So we start on the category of finite G sets. That's these are the basic building blocks. So a Tambara functor or a G-Tambara functor is a, say, function underline R for ring from the category of finite G sets. I call it like this: finite sets with a G action, 2 commutative rings. And then you want certain compatibility relations. Well, it's called a Tambara functor, so maps of G sets should do something. But then you have other things that are important. So if I have a finite G set, I assign to it a commutative ring, and then for a map of G sets from X to Y, I get 3 induced maps. So, and these are exactly these 3 structure maps. Restriction goes backwards, or the other ones go with the flow, but they are very, very different in what they respect. So I get a restriction map, and that's a ring map going backwards. So Ry to Rx. Then we have a transfer map going with the flow, but only preserving the addition. So we get a map of abelian groups. And last but not least, the norm, also going with the flow. But this is a multiplicative map, and unless you're in very, very special circumstances, it's not additive. So in particular, this doesn't induce a map of a Being group, so there are some hiccups caused by this. So this is the norm. Right. So, of course, there's a different way of saying this. Well, if you have the identity map, it shouldn't do anything. And then you could also just say that R gives a contravariant functor, whereas T and N give covariant functors. So that's maybe a shorter way of packaging this. But all share the same value. R of x. So composition does what it has to do. And then there are some more axioms that tell you more about the interaction of these maps. And this is pretty complicated. But first of all, you want a decomposition property. So if you have an inclusion of G sets that witness that X is the disjoint union, then the same happens on the level of Tambara functors. You can split R of X into the product of R of X1 and R of X2. And this is important because you can decompose every finite G set into orbits, and then this just means it's determinate on orbits. So it maps, this is actually a product in the suitable category, but so it sends disjoint union of G sets to products. This is one thing. And then you want to know how restriction, trace, and norm interact. And for this, you look at certain pullback diagrams, and I always mess this up, so let me fix the notation. So, okay. So if I have this, and this is a pullback, then the idea is that you compare these two ways of moving, and this then tells you what to do, because some of these arrows go against the flow, so you have to use restriction, and the others go with the flow, and then you have two versions what this induces. So you get one diagram for this, so going with the flow, say norm, restriction, S, restriction, norm, and same for the trace. So these interchange. So what's missing is you might want to pass a norm by a transfer map. I told you at the very beginning that this ends up in commutative rings, but you can actually define the ring structure using maps of G sets. Namely, the fold map gives you, if you have G mod H, disjoint union mapping to G mod H. Transfer this as addition, norm of this as multiplication. So you want a sort of distributivity law for moving transfers and norms along each other. This doesn't work on the nose. It doesn't always work. There are some restrictions. And I won't explain that talk. This term here. So just beware, not every commutative diagram will be good enough to give you an interchange law. There are restrictions, there are heavy restrictions, how they look like. So we start here. And here. So these are diagrams that are equivalent to certain pullbacks that I don't specify, where here one of them is a restricted product, and then you have some E is then an evaluation map. So, but let me not specify this. So the idea is that, again, you move that way. So you compare these two ways of walking around. But now it does matter what you do. I mean, there you had just two options what to do, but here you don't. So you get that norm F composed with transfer G is the same as transfer H composed with norm F par. But you pay, you have this extra term restriction along E. So you have to go backwards first and then here. So this is called distributivity. If two of these are fold maps, then this actually gives you an interchange law for a multiplication and addition, but only in this particular setting. So what is the upshot? This is like a Mackey functor with extra structure. This diagram here corresponds, if you know what a Mackey functor is, to the double coset formula. And there you don't have this extra condition, but you have the splitting for direct sums. So there are things like this. So you get a forgetful functor from G-Tambara functors down to G-Mackey functors, just by forgetting stuff. This was the one. Pardon?
Is the norm required to respect the unit or something like that? Or?
Yes, it's a map of monoids. So yeah.
Okay, so we have to remove the zero.
Yeah, you can say that. Well, it's a monoid like that, right? So it doesn't matter. Okay. Yeah. So the unit is actually given by the inclusion of the empty set for trace and norm, so or transfer norm. I always say trace, yeah. So we do have a forgetful functor. Say from G-Tambara functors down to G-Mackey functors. So if you forget the multiplication and the norms, and the rest of the structure is there, and you only end up in abelian groups. So nothing wrong with that. There's a semi-version where you don't insist that the additive thing is a group. You're happy with being an abelian monoid, but I want the full structure. So this is that. We can decompose every finite G set into orbits, and then this second condition up there tells you that our is determined by the value on orbits. And that is then leading to the fact that you find sources where this is defined in terms of saying what happens on orbits. Or if you go to the algebra literature, so they might even say, they might call this R underline of H, sort of putting things upside down. For instance, Thevenot's web or so. I mean, you might find that notation. So this is important in representation theory, group cohomology, whatnot. So it shows up all over the place. Yeah, so that was that. So let's do some examples before we go to Loday constructions. So I'm really grateful for Emanuele for mentioning all these things before. So if you have a commutative ring with involution, or more generally a commutative ring with some G action, you always get a Tambara functor. So our commutative ring with G action, then you can define the fixed Tambara functor where the value on a standard orbit is just the fixed point of R under the H action. So that's a particular case. Then you can sort of spell out what the maps are. Restriction is inclusion of fixed points. Transfer will sort of add things on expanding things on cosets and adding them. Norm will expand things on cosets and multiply the values so that you end up in the fixed points again. So this is pretty explicit. I will only need a special case of this. Nobody prevents you from taking the trivial G action. And then you get something that's called a constant Tambara functor. And there, all restriction maps are just identity maps. Transfer maps is multiplication with the index, and the norm is taking the power, something to the power of the index. So it's a very explicit thing to do. So this is what will show up today, later. Wrong world. So, and another very important thing is the Burnside Tambara functor. So, this is called R underbar, and quite often, this of course depends on the group G. Quite often one suppresses this from the notation, which can be extremely confusing. So what is this thing? You take finite G sets over a fixed G set. So isoclasses of finite G sets over X. And then you group complete. I mean, you have a sum in this category just induced by a disjoint union, and then you can group complete this. Here the structure maps are, I mean, restriction is sort of by taking the fiber product, you pull things back, as you always do. Transfer is just composition, and the norm involves, again, something that I suppressed when I didn't tell you what exponential diagrams were. This involves the dependent product construction. So maybe one thing to take from this example is that here restriction and transfer are easy and norm is a bit involved. So why is this an important gadget? So for rings, the integers are initial. If you work in G-Tambara functors, then this is the initial object. So AG is initial and G-Tambara functors. So I will really need these two examples.
So in general, is there any adjunction between maybe G sets and the Tambara functors?
You have tons of free functors, and they're all different. And this is, yeah. And I decided not to include free functors today. So yes, there are adjunctions. Yeah. And they don't always behave as you would like them to behave. So this is this. Right. So with Ayelet and Fuling, we did some work on Loday constructions for commutative rings and commutative ring spectra. And then we thought about what happens for fiber products. And then you naturally end up considering things with group actions. And so, I mean, Fuling is an equivariant person, so for her it was quite natural to go then all the way. So why not do Loday constructions in this equivariant setting? But maybe let me remind you what the classical thing is. So say you have a finite simplicial set. And R is a commutative ring, maybe spectrum, doesn't really matter. Then you can tensor R over X, so you can form the Loday construction of R with respect to X. This will be a simplicial commutative ring, and in degree n, it's just you take as many tensor powers of your ring as you have elements in Xn, and you just form this tensor product. Note that unless X is very, very special, you really need the commutativity here because points in X come from all possible directions. So if you have a map of sets, say the simplicial structure maps, if you take the phase maps, these are induced by the phase maps of X, so you go from Xn to Xn minus 1, and it will just multiply everybody together that had the same pre-image. And of course there's no ordering, so you need commutativity so that this is well defined. If you don't have a pre-image, you insert the unit, and that gives you a simplicial commutative ring. And you all know special cases. So if X is S1, this gives Hofstede homology. Well, the simplicial thing, if you take Sn for n bigger than 1, you get higher THH of R for higher dimensional spheres. Or if you take the torus, then this actually does relate to K-theory. So this is torus homology. You have a trace map from K-theory to THH. If you have an n-torus, you get an iterated trace from iterated K-theory down to torus homology. So these are sort of important cases, but now the question is, what can you do about simplicial G-sets? So say finite simplicial. You can always can't extend, but let's stay finite.
So maybe this is slightly confusing. Are you taking for example, the efficiency, or is the geometry realization of this simplicial object?
It doesn't matter. You can. So if you really have a ring, this is a simplicial commutative ring, and then you can take its homotopy groups maybe, or you want the realization and take the homology. I mean, it doesn't really matter. You can take the associated chain complex. For spectra, you would canonically take the realization, and that would end up in commutative ring spectra.
No, but the point is that somehow this does, after taking geometry realization, this doesn't depend. It only depends on the weak homotopy type of X.
Yes, it does. But this is also true in algebra. There you can run a spectral sequence argument. It actually only depends on the integral homology type of X, even less than the homotopy type. You need the integral homology of X as a coalgebra with its coalgebra structure. Right. So what about finite G-sets? And then two people saved the day. So there's something like you can characterize commutative monoids by saying that they give you functors from finite sets to K modules by taking the tensor product, and then surjective maps would induce multiplication, non-surjective ones insert units. And there's a similar notion developed by Mike Hill and the other Mike about how you can characterize commutative monoids in an equivariant setting. And so the corresponding theorem is by Kristen Mazur and I probably should put years here. This is thesis work. So this is Kristen's thesis on where she investigates CP and Tambara functors, and then there's a slightly more general construction for general finite groups by Rolf Hoyer, also thesis work. So what do? They say you can tensor finite G-sets with Tambara functors, and you get something well-defined. It behaves as it maybe should behave. So there's a functor finite G-sets and G-Tambara functors, two Tambara functors, such that, so I denote this by X tensor. And what you do is you have a wish list of things that says that this behaves as it should, and then they prove that it actually does. And this takes a lot of work. So I told you that Tambara functors internally map disjoint unions to product, but if you tensor this, you want also to know what happens to disjoint unions. So if you take the disjoint union of two finite G sets, then this should go to the corresponding symmetric monoidal structure thingy. So that's the box product for Mackey functors. So think of tensor product. So in Tambara functors, that's actually the coproduct. And this is what happens here. For commutative rings, the tensor product is also the coproduct. And you just say coproducts in sets go to coproducts in Tambara functors. That's a reasonable wish to have. And then also, if you have a coproduct of Tambara functors, it also maps to the coproduct. So these are sort of coproduct formulas. And then you want two more things. Products should go to iterations. So x times y tensor R should be the iterated tensor product. Of course, there's a symmetry here. And you want a sanity check if you really don't have any G action, if you have a trivial G action, just a bunch of points, then you want the old structure. It's just tensor powers. So if X is a G set with trivial action, then this is really given by the tensor product in this category. One way of thinking about this is also it comes out of this here. This is just a bunch of points then as a disjoint union of G sets. So you just get X copies of R. So it's very similar to that formula here. But the important thing is that this is functorial in both things. In particular, it's functorial in the G set. So if you now have a simplicial G set, it will just move along. So you get something well-defined. Doesn't want.
And the other direction. And then down.
Right. But this is the wrong. Okay. So if X is a finite simplicial G set, and R is a G-Tambara functor, then we define the Loday construction. And I usually denote the G with the Loday construction to signal that this is now the equivariant thing for X of R in simplicial degree n, just to be Xn tensor R. So this will be a simplicial object in G-Tambara functors just because they proved that this is functorial in the G set, so simplicial structure maps, induce maps of Tambara functors, if you go along. So this is sort of the Loday construction. For R with respect to X. So far, I only told you that they did this. I did not tell you how it looks like. So you might ask, well, what do you get? So Xn is a finite G set, so it decomposes into some orbits. So I only have to tell you what happens on one of these things thanks to axiom, the first axiom. So, and in both works, what they showed is, well, this isn't joint work, but so if you take G mod H, tensor R, this is restriction and then norm. So R was a G-Tambara functor. You restrict it down to H, and then you blow it up with a norms construction up to G. And this norm construction is actually the main part where their work goes into constructing this norm. So Kristen does this explicitly for cyclic being P groups, and then Hoyer does a general construction in terms of Lefkan extensions. So this is where the work is. In the explicit description of the norm, this norm functor is left adjoint to restriction on the level of Tambara functors. There is a norm construction for Mackey functors, but there it is not a left adjoint. So this is a pretty intricate construction. So roughly you can think of this as being index H and G copies of whatever you plugged in, and you have the tensor induction action. But the exact formula is way more complicated. So I should put an isomorphism here. If you take this as a definition, you get into trouble, but or you have to show more. So if you want, you can make this completely explicit, and I'll do so in some examples now. Questions? So what is a sanity check? If there's no group, you should better get the old stuff back, right? It would be weird if you introduced homotopy types for things that don't really exist. So the first thing isn't really an example. It's just a sanity check. So if you have a finite simplicial set and you view it as a simplicial G set with trivial action, and if you just plug in a commutative ring and you view it as a G ring with trivial action, then this should not give anything new. So this is the setting, finite simplicial set. So we put the trivial G action on it, and R is a commutative ring without any G action. So what can I do? I can take the non-equivariant Loday construction, the thing that's still there, just use the ring structure and the set structure of X. This is the simplicial commutative ring. So in every simplicial degree, I can take the constant Tambara functor on that. So this was example 1 dash. So I just say you are now equivariant, but with the dumbest structure that there is. And then you can compare this to the Loday construction, where X still has the trivial G action, but now you view it as a G set, and you take the constant Tambara functor on R because you can't really do anything else. And then you sit down and check definitions. And then you say, phew, they're isomorphic, so all is well, right? We didn't introduce anything superfluous. So except for the fact that this might be hard to parse, so this is just, this is the new equivariant Loday construction on the trivial Tambara functor, where X has the trivial G action, and you just get the constant Tambara functor, the constant simplicial Tambara functor on these things. So that was good. Oof, nothing bad happened. So what does this Loday construction see? Well, now you have sort of two variables. You have the Tambara functor and you have the G finite simplicial G set. So, and one example I want to do tells you, well, it heavily depends what the isotropy behavior is. So this is what you want, right? You want to see what fixed points are, what stabilizers do. So, and Tambara functors are complicated. So let's just do the group of order 2. That's bad enough. Then the only stabilizer is pretty drastic. So, yeah. So let's do the group of order 2. The integers are initial in the category of commutative rings. And the commutative ring can be viewed as the restriction of the constant Tambara functor. So, so if I norm this up, I get the initial object in C2 Tambara functors. So that's the Burnside Tambara functor. This also has an explicit nice formula, but I don't really need this. It's just initial objects go to initial objects because that's the left adjoint here. So what does this say? This is also the value of the free orbit if I tensor the free orbit with a constant Tambara functor on the integers. So, and if you have this behavior, you get that for a group of order 2 where either you have a fixed point or you don't. The value of the Tambara functor of this constant thing just is a 0-1 decision. Do I have a fixed point or is everything free? So these are the Hungary fixed points. So X is any finite simplicial C2 space, simplicial C2 set. And I take the constant Tambara functor on the integers. And then what I get for the Loday construction, for the equivariant Loday construction, only depends whether I'm always free, then I get the Burnside ringy thing, or so that's, or so the fixed points are empty. Or if I have a single fixed point somewhere, I get my ring back. And this is meant as the constant simplicial Tambara functor on that thing. So it's just everywhere the same thing. So, and the proof is easy. Well, the proof is on the blackboard. If I have C2, if I have a fixed point, then I just get this. This was one of the defining formulas. This is just the finite set with 1 point, so I get the one-fold box tensor product of that thing. And if I have a free orbit, I get the Burnside Tambara functor. And the only thing you have now to think about is that this propagates. But this is a simplicial C2 space, so set. So if I have a fixed point somewhere, it is moved up in all simplicial degree, and it's moved down with a phase map. So I have it everywhere. And then the only thing that you have to calculate is, well, this doesn't do anything. This is the unit, and boxing constant things gives the tensor product, but Z tensor Z is Z, so these two formulas together with this gives you that behavior. So these weren't actual examples, right? So let me do an honest example. As two of the authors are in the audience, I thought I'd do that example. So I take a simplicial model of the one circle together with a rotation by the cyclic group of order n, and n is not trivial, so there's actually something happening. So I have to fix notation, so I take the cyclic group of order n, and I fix a generator, and as Mike and Tina call this gamma, we call this gamma. So we go into a point, then I have a defining edge here. This was the hardest bit to find a notation that made the simplicial structure easy to describe. And it took us several days. So, and then you just move your points around, you move your edges around, and eventually they come back to you. So this is gamma to the n-1, which happens to be gamma inverse. So that's a simplicial model of S1 with a rotation action by the cyclic group of order n. So what is the good thing? Everybody is a free orbit, right? The point gives a free Cn orbit. The edge gives a free Cn orbit. Everybody's happy because then we know what we get. So So the rotation circle in degree k only has 3 orbits. I will explain what the notation is. So I've got k plus 1 orbits, and x0k is really just the degenerate thing on the base point, and I'm going from 0 to k, so that's correct. And the other ones mix the degeneracies. So I have first the S1s and then some S0s to make up for the correct dimension. This is an edge, so this has to sum up to k minus 1. So these are the orbits that I get. And if you then sit down and calculate the simplicial structure maps, I mean, these are just phase maps, so the simplicial identities tell you what you do. You get on the Loday construction, everybody is free. So if I evaluate this in simplicial degree k, I get I from 0 to k, and I get Cn mod E tensor R. So I get k plus 1 copies of norm restriction of R. And the phase maps are almost as in the Hochschild complex. But you have one twist, so the last phase map doesn't only pull the last thing to the front, it also induces an action. There's something I sweep under the rug. You have a choice about the Weil action, but if you pick the right one, this is what happens. So I have Loday Cn in degree k to the same thing in dk minus 1 with di, and from 0 less or equal to I less than k, these are the, say, Hochschild phase maps. Well, you have the box thing instead of a tensor, but nothing really happens. But for dk, you get the twist, so the thing you know from the Hochschild complex, the thing has to move to the front. Let me call this tau, so that's just the twist. But then you act by gamma on the very first coordinate, and then you multiply. So this tau is just that one, and then you have the action here, and then you multiply the first 2 components. So this is the full simplicial structure. So, and what happens is, and the other thing you should notice, I only have 3 orbits, so I only have norms. I never shrink an orbit to anything non-trivial, so I don't need the multiplicative norms. I only need the underlying green functor. I only need a multiplication on my Mackey functor. So, so what we get is that this thingy is actually isomorphic to the cyclic twisted nerve of R of the underlying green functor. And that's the twisted cyclic nerve by, oh God, Blumberg, Gerhardt, Hill, Lawson. Yeah. So you get an isomorphism on the nose, so I don't have to tell you what this is because it's really that. So, but this isn't R, this is on the norm thing. Sorry for cheating here. Yeah. So that's on norm restriction R. But if you want to get their formula back, we also get, if I divide, so CK subgroup equals CN, if I divide that circle by CK, then I get their relative version. And now, just on the restriction. So in particular, if I divide out by the full Cn, I really get the original description without all the restriction norm things added. So so for the trivia group, you just norm up again, so this gives the old result. But if you have the full group, you get that one. So I mixed. I think I need a restriction somewhere. Yeah. So I need that here. That restriction here. So this gives this. And maybe as a last remark, at the free level, so if you have this Tambara functor, you have all this complicated stuff, but at the bottom you have the value on the free orbit, and that always behaves like algebra. And what we get here is that then this really looks like the ordinary Hochschild homology. This is isomorphic to the nth subdivision of the ordinary Hochschild homology of the commutative ring that you get at the free level. So as a whole Tambara functor, this does give something interesting, but at the free level, it's really just ordinary Hochschild homology. You get the same homotopy type. It just looks weird. I mean, you see that you have an n-fold subdivision of the circle, and you just have to rearrange the vertices to make that work. So we can also do other examples. We can also do the flip circle that's then hopefully related to real Hochschild homology. But that example, I mean, I had to choose what it talks, so I didn't talk about that. And we can do calculations about suspensions if you either suspend and you leave the points alone, or if you suspend and you flip the suspension points. These are also examples that we can handle. So the upshot is, well, this works. It's sort of doable in calculations. But the hope is, of course, to relate this to topological definitions like real THH or other group actions that you might. So group homology theories for genuine G-commutative ring spectra. Thank you.
I was confused about, because you mentioned real THH, and so I mean you have S sigma, which is a simplicial finite C2 set. But I mean, it seemed like up here. I mean, maybe I misunderstood what you're claiming here, but.
No, I mean, if you take that,
Just saying the case indices or.
if you take that circle,
Yeah.
that is sort of S1 with a flip action, and that makes sense if you take a ring with involution, and that example should be related to real Rothschild homology or real THH if you do this for spectra.
Right, but I guess so. Here you're not claiming that is this just in degree K? You're claiming?
Pardon?
In the statement up here, it's just in degree K, right? So
Well,
you're saying
what?
that the whole complex is just concentrated degree zero.
I don't see what you're pointing
On
at.
the top left board, I'm just confused about the claims.
On the left or where?
The top left.
Okay.
Like the proof just seems to be for.
I said, I only said it, this is the constant simplicial Tambara functor on this value. So this object is a simplicial Tambara functor. This object is a simplicial Tambara functor, and I claim it's in both cases it's constant. If you have a fixed point anywhere, it gives you the Tambara functor back. If you're free everywhere, it gives you the Burnside constant simplicial Burnside Tambara functor. That's the statement. Sorry.
Another question about the Hungry fixed points. Do you know what this looks like for CP for like an odd prime P?
Well, there you also don't really have any other subgroups, so you should get the same thing. But as soon as you have possible other isotropy, then yeah, things get complicated. So I wouldn't. Yeah, so C4 is a different story.
I have a question. So Loday, in Loday's original setup, maybe he kind of like the gamma object or whatever, use this to cook up some operations on cyclic homology and Hochschild homology. Is there any equivariant version in your setup?
Probably. I mean, this.
At least rationally. Ignore the technical.
Well, I mean, this is the more general question. I mean, this is natural in the G-simplicial set. So whatever you can do there gives you something induced on the Loday construction. So the only question is, can you calculate what the effect is? And I mean, for instance, when torus homology was invented, the hope was that you get interesting group actions. Or you could ask, is there a non-trivial map from third order topological Hochschild homology to second order THH induced by the Hopf map? But in many of these examples, these things turn out to induce trivial maps. So the exploitation of having something like the Eulerian idempotence given by a sort of combinatorics of S1, yeah, you can do this. But I don't know of any convincing example. Maybe Bjørn, how far is there? If Bjørn says so, then yeah. I mean, yeah. So yes, you can do things, but it's sometimes hard to determine what you get. And in some particular cases, we know it's trivial. So.
More questions? Yeah.
You know what happens in finite? So if you take this Loday construction for a finite space, and then you hit it back with phi 0, is there an intrinsic algebraic?
Well, I mean, these people the cyclic, twisted cyclic nerve people use this to say, we call pi naught the width vectors of the green functor, right? So there is this structure. For general X and general R, it depends on so many things that I don't have a good answer. I mean, we spent quite some time trying to relate some version of HH1 to Kähler differentials and eventually gave up. So, I mean, yeah, usually if you give a talk about these things, then pi naught is usually easy. You can say something about pi 1, but here, I don't know.